Now we will try to learn how to solve line integral of a vector function using a simple example. To start with, we must define a line integral. So if we consider a vector function v bar, which is a function of x, y and z in general, then in the coordinate frame x, y, z, we can have a point to begin with, call it as A, and we can imagine a path leading to some other point B. Of course, these 2 points can always be represented by vectors A bar and B bar. But let us just forget about those vector notations first, as we understand this concept of line integral. Then we can assume an infinitesimally small line element dl bar. And as we have already discussed, this dl bar is just dx x cap plus dy y cap plus dz z cap. Then we define a line integral over this particular path as integral from a to b. Let us call this path as path p. So we will label or indicate that this is the specific path we are going to take while we integrate. So the line integral from lower limit a to upper limit b over path p is just v bar dotted with dl bar. This is called as line integral of v bar over specified path p from a to b. If the path is closed, that is, somebody starts from a point A, travels in space and returns back to point A again, then this integral is just denoted by a different notation. This is called as closed integral. So v closed integral v bar dot dl bar is going to give us a line integral over a closed path. In order to understand how to solve this, let us take an example from the book by Griffiths on electrodynamics. Consider a vector function v bar of this type, namely v bar equal to y squared x cap plus 2x into y plus 1 y cap. Now note that in order to simplify this, we are just avoiding the z component here. So z component is absent. So let us just erase this, and we consider 2 points in space A and B. So A is a point denoted by coordinates 1, 1 and 0, whereas B is a point denoted by coordinates 2, 2 and 0. Now one should note that even here as well, we have set both the z coordinates to be 0 for these points. So z axis need not be taken into account as it does not appear in v bar as well as in the coordinates of the points A and B. So the line element, which was already defined as dx x cap plus dy y cap plus dz z cap, gets simplified to just dx x cap plus dy y cap, as we have eliminated the need for z coordinate and it is no longer necessary for this particular problem. Now what we have to do is we have to integrate this from A to point B. That should give us the line integral v bar dot dl bar starting from A to B. But here we have not yet chosen the path P. So we have to define the path as well. For that, we will represent these 2 points on the coordinate axis x and y. So point A, let us just label these 2 axes with proper numbers. The point A lies here, having coordinates 1 1, and z coordinate of course is 0, and point B is somewhere here. So we can try using different paths in order to reach from point A to point B. So one of the paths is like this. First we move along the x direction, the positive x direction, and then we move along the positive y direction. So let us call this as path 1. The other way to do this is we directly travel from A towards the direction of B and reach point B. So label this path as path 2. Now we will try doing the line integrals for both of these paths. Let us just choose path 1 first. And let us just represent this diagram again. We should note that this value of x coordinate is 2 and this value of y coordinate is 1. Starts from A and reaches to B. Now this path 1 can be subdivided into 2 segments, namely a horizontal segment, let us call it as segment I, and a vertical segment which is labeled as segment II by Roman letters. So along segment I, we see that the y coordinate is fixed. It is having value equal to 1. Further, since we move only along x direction, dl bar, which was originally dx x cap plus dy y cap, gets further simplified to dl bar equal to dx x cap. We should just recall that v bar is given as y square x cap plus 2x times y plus 1 y cap. Now for this particular segment, we see that dl bar is just dx x cap. So v bar dot dl bar would be, so this is just 0 times y cap. So dot product of this with this gives us y square into dx plus 0. Since we have a 0 here, so the dot product gives 0 into dy, anything. So let us just write it as 0. So what we have is y square dx as v bar dot dl bar for the first segment I. Further, we also know that y is just equal to 1. So this is further simplified to 1 square dx, which is just dx. So now integral v bar dot dl bar is simply integral dx. And we see that for this segment I, x coordinate runs from 1 to 2. So the lower limit is just 1 and upper limit is 2. Integral dx is just x with lower limit 1, upper limit 2. So we have upper limit minus lower limit. So this is equal to 1. So this is the case, or this is the value of line integral for the segment I. Now let us continue this to solve this line integral for segment II. So for segment II, we see that the line is vertical, so we move only along y direction. So in this case, dl is obviously going to be just dy y cap, as there is no change in x direction involved. Further, we see that coordinate x is fixed and is having value 2 for this particular segment. So again, if we recall that v bar is y square x cap plus 2x times y plus 1 y cap, we see that v bar dot dl bar is just 0 plus y0, because here we have 0 x cap, right? So when we take a dot product of this with v bar, the x component disappears and y component is present. It is just 2x y plus 1 dy. And if we further substitute the value of x here, we get 2 into 2 into y plus 1 dy. So x is equal to 2. Hence, this v bar dot dl bar is 4 times y plus 1 dy. So if we now integrate this v bar dot dl bar, we get integral 4 times y plus 1 dy. If we check the limits of y, we see that y runs from 1 to 2. So the limits for y as well are from 1 to 2. Now if we integrate this, 4 is just a constant. Integration of y is y squared by 2. Integration of 1 is y, lower limit, upper limit. So 4 into upper limit is 2 squared by 2 plus 2 minus lower limit 1 squared by 2 plus 1. And this gives us just 4 minus 3 by, just a minute. Oh, there is a slight correction here. Suppose, no, right. 4 minus just 1 by 2 plus 1, that is 3 by 2. Now we have 4 into 8 minus 3 by 2, which is 4 into 5 by 2, which is 10, right? So we see that the total line integral from a to b v bar dot dl bar is line integral for segment I, plus line integral for segment II. So this is just equal to, if we recall, this value for segment I was just 1. The value for segment II is 10. So the value is just 11. This is how we solve the line integral. Now if we recall, we have also included, just a minute, another path to reach from A to B, and that path was just a straight line path. So if we try to solve the same line integral from A having coordinates 1 1 going to B having coordinates 2 2, this was the second path. Now for this, both x and y are simultaneously changing, so we need to have a relation between x and y. We see that this path is a straight line path, so it must have this particular equation of a straight line in general. Now if we see that if we substitute the values for y equal to 1, we have x equal to 1, which is point A. So if we use this, 1 is equal to m into 1 plus c. So m plus c is just 1. Now for point B, we have y equal to 2 and x equal to 2. So if we use this here, we have 2 equal to m into 2 plus c. That is 2m plus c is equal to 2. Now if we solve these two equations, we just multiply this by 2 to get 2m plus 2c is equal to 2. If we add this or subtract these two, we get 2c minus c is equal to 0, that is c equal to 0. So the intercept on y-axis is 0, and that is clearly visible from if we extrapolate this straight line. We see that it intersects the y-axis at 0. And if we substitute back the c into any of these two equations, we see that since m plus c is 1 and c is 0, we get m is equal to 1. So these are the values of those constants in the equation of straight line, m equal to 1 and c equal to 0. So we get y equal to 1 into x plus 0, that is y is equal to x. So this is how x and y are dependent when we follow this particular path. So yes, we have now with us relation for y in terms of x. So if we see v bar dot dl bar now to be equal to y squared x cap plus 2x y plus 1 y cap dotted with dx x cap plus dy y cap, we get y squared dx plus 2x y plus 1 dy. But we see that y is equal to x for the given path, so dy is equal to dx. So either we can eliminate y or x as per our choice of freedom. Let us just eliminate y. So we can replace y by x and dy by dx to get x squared dx plus 2x x plus 1 dx. So whenever we see y, we have replaced it by x and dy by dx. So this gives us x squared dx plus 2x squared dx plus 2x dx, which is equal to 3x squared dx plus 2x dx. So this is v bar dot dl bar. So let us just integrate this now. So integral v bar dot dl bar is equal to integral 3x squared plus 2x dx. This is what we have used here. And further, we see that when we move from point A to B, the value of x changes from 1 to 2. So the lower limit here is 1 and upper limit is 2. This is equal to 3. X squared integrated gives us x cubed by 3 plus 2. X integrated gives us x squared by 2 between lower limit and upper limit as required. So this is just x cube plus x squared between 1 and 2. So 2 cube plus 2 raised to 2 minus 1 cube plus 1 squared. That is just 8 plus 4 minus 1 plus 1, which is again 10. Now if we recall the two integrals, we have seen that if we follow this particular path, segment I gives us value 1 for the line integral, segment II gives us value 10 for the line integral, causing the total line integral to be equal to 11, whereas this was for path 1, whereas if we follow path 2, the value of line integral is 10. So we see that if we change the path, the value of line integral may change as well. But of course, this is not true always. There are certain functions v bar for which the line integral is path independent. Such functions are called as conservative. If we try to have the value of closed integral, so if we go from a to b by following path 1, and if we return back from b to a by following path 2, the closed line integral in that case would be integral for path 1 v bar dot dl bar plus integral for path 2 v bar dot dl bar. But we should note that when we do this, we just reverse the direction for path 2. So we go from a to b by following path 1, but we return back from b to a. So if we revert the direction of travel, we must also revert the direction of this value of line integral. So this means that this is equal to 11 plus minus 10. Since earlier we calculated this value when we traveled from a to b, and now we are traveling from b to a, so we put a minus sign here. So this gives us 1. So the closed integral v bar dot dl bar for this particular direction of paths is equal to 1. This is how we should solve line integrals. Of course, we need to have a practice of solving such problems. Thank you very much.